screen. You're an expert at this. Thank
Is
you.
that working?
It is.
And can you all hear me?
We can, or I can.
Good enough. Hi, so thanks for having me, and I'm looking forward to this conversation. And I'm going to be talking about, since I work in infrastructure facility at the NCRIS-funded Australian Plant Phenomics facility, we spend a lot of time thinking about what can be enacted at the national scale to really enable the sorts of outcomes that John was talking about. And I think, as John mentioned, if you look at what we're facing, we really face a triple threat this century. In food security, there are 8 to 9 billion people on the planet who are going to need food for the next century. And there's an ever increasing demand from increasing consumption and population growth, as well as for animal feed and auto fuel. And at the same time, we're experiencing decreased production, both from soil and water degradation alone, as well as the impacts of climate breakdown on top of that. On the biodiversity side, we've seen massive habitat loss and fragmentation and problems with invasive species and climate impacts in the last century. In the last 45 years, there's been nearly a 70% drop in global species populations. And it's important to note that 70% of this is due to land use impacts from agriculture. And on the climate change side, of course, this is the thing that is the backdrop to everything. And we really need to understand that renewables are necessary, and ending emissions is necessary, but they're not sufficient. So we really need significant carbon drawdown in addition to ending emissions. And agriculture plays a significant role of all of these issues, both in causing them and in potential solutions. And so it's an interesting and exciting place to be involved with this. Now, again, carbon neutral is vastly insufficient, and carbon drawdown is a necessity. And if you look, there's a couple of the scenarios that came from that 1.5 degree IPCC report, and you can review them at the climate change recovery site. But the bottom line is to need better than a two, to get a 2 out of 3 chance of keeping global warming below 2 degrees C, which is pretty catastrophic. We have to be reducing our gross carbon emissions by 10 gigatons a year per decade for the next 80 years. And we also have to do this while sequestering significant additional CO2. So this is really a serious challenge, because we need to be starting to go carbon neutral now in a major way. And none of the scenarios that seem at all likely can happen without also significant carbon sequestration. So there's a huge role for carbon drawdown in all this. And changing farming practices in Australia can contribute to carbon drawdown. And so I think this is really exciting in terms of thinking of what we can do with digital agriculture and better management practices. Globally, agriculture accounts for 12.5% of greenhouse emissions, and a fair bit of that is land clearing, but also a lot of it has to do with annual cycles in production that release a lot of carbon emissions. But what's interesting is within Australia, the annual carbon drawdown and release from the land sector, so from photosynthesis essentially, accounts for more than the annual carbon emissions from the energy sector. And to understand that better, you can look at if you look at the carbon uptake from 2009 versus 2010. So in 2010-11, there was a really strong La Nina, and there was a 40% carbon emissions reduction globally, and 60% of that came from Australia. And essentially that all came from the center of Australia that's normally quite dry, greening up and sucking all of that carbon out of the air in huge grasslands. And of course, in that context, it just gets re-emitted because the roots don't really sequester much carbon. The rest of it burns or just decomposes. But this points to the fact that photosynthesis and agriculture has a huge potential to be doing actual carbon drawdown if you can shift your management practices so that the roots are pulling carbon underground in ways where it stays. You can be doing biochar, you can be growing trees in better ways. So there's a lot of potential here for us to improve our to improve agriculture, to improve emission scenarios in Australia. But again, this is a largely unsolved problem, even though there's a lot of good work. And so this is really where we can start to tackle this problem. And from my perspective, thinking about how we can tackle some of these challenges with national infrastructure, I think what we need to build is an open infrastructure platform for managing farm, forest, and environmental data within Australia. that can deliver turnkey data capture tools, data visualization, analysis, and fair data sharing that can lead to improved decision support. And we can do this because the technologies exist, right? There are IoT sensors that can push precision environmental data to the cloud for every farm. Modern farm equipment records centimeter resolution positions for all seeds and post-planting treatments on most farms, or could be, without too much effort. We don't have automated drone flights yet, but we're getting there. And so they can produce, every day your drone can wake up and scan your entire farm at high resolution in 3D or any field sites or land management sites. There's sub-meter resolution satellite that can record multi-spectral indices about crops. And I think, a lot of people, when they hear this, it's scary because of the ongoing privacy issues there are on the internet. But we really can build privacy and by design if it's done correctly. So things don't have to be this way. These systems can empower farmers and land managers to own their own data, contribute it to national anonymized data sets, and share it with whom they choose rather than the vendor owning people's data by default, which is how it usually works these days. And so building a system like this enables researchers and breeders to do really continental scale analysis, right? Because you're starting to get farm, data from significant numbers of farm across the entire country, as well as to have core infrastructure for doing better field trials with this type of high precision monitoring. This would provide farmers with low barrier entry to access to the benefits of digital agriculture. And it also creates a much healthier ecosystem for industry and for small startups, because currently when startups want to play in this field, they sort of have to build the entire pipeline from the hardware on one end all the way to the analytics on the other end. And if a lot of the core problems have been solved by good data standards so that every sensor spits out data that anyone else can interact with if they have access to it, a lot of the technical problems that startups have to solve and that industry have to solve just get fixed for everybody, and they can focus on more innovative things around, how do you build a really good sensor, or how do you build really good at downstream analytical tools? So what are some of the technologies that we can use to build this future? This year is an interesting one for people in NCRIS because they're doing a year-long road mapping process, which is looking back at the last decade of NCRIS investment and then looking forward for the rebid in 2023, when they're going to decide how to spend about $1.6 billion on infrastructure. And so as part of this, I was thinking, what was the landscape like when NCRIS was first divisioned in 2004? And how have things changed? And it's really amazing because if you look at the period from about 2005 to 2008, all of the technologies, or the start of the technologies that really determine how we do everything day to day in our lives are from that time period. So Google Maps and Google Earth, this ability to zoom into anywhere on the planet that we take for granted now, the ability to talk to anybody via email, communicate with your friends, put any video of anything online, Twitter, scalable cloud compute, iPhones, touchscreens. 15 years ago, none of those things existed. And now here we are where that's what we do everything with. And so I think it's exciting both to understand what a transformational change that was, but also to see that we're now in a similar period of accelerated innovation and taking that thinking now 10, 15 years in the future, what will that look like? So some of the emerging solutions that I think are really interesting, I'll talk about now. One of them in particular is high resolution, high frequency satellite data. So, it used to be you either got high frequency but low resolution, or low resolution and high frequency. But the new round of CubeSats and similar small satellite products that are being launched are really crazy. So the Maxar Legion system that's going up this year will provide 29 centimeter pixels, right? That's that big, up to 15 times a day, repeat over 5 million kilometers per day total. So 5 million kilometers on the planet, places you can repeat 15 times. If you have a look at Planet Labs, they have a nice interface that you can log onto for free, and they have some really good tools for looking at this sort of data. But if you imagine this in the Australian context, if we had a similar satellite system up, you could image all of the broadacre farmland multiple times a day, or the entire country every single day at, basically plant resolution or smaller than that. And to me, that's just an amazing tool, right? It means we can just be knowing what's going on in every single farm in Australia continuously. And the systems like this This one, the Max Arlesian one, was about $825 million. That seems a lot of money, but if you think about the gross domestic product or the outputs of all of the different people that would be impacted, that farm, cities, mining, land care, that's billions of dollars of GDP a year. And so the value of something like this, I think, when you put it across all of those domains, is really far greater than the cost. But it's important to understand that current satellites that provide this data are not free like the US Landsat data. There's a high end cost to users and limited access. And so this is where you can imagine that if something like this was really considered a national asset, there'd be a lot more value provided to the farming sector. Of course, once you get data sets like this, it's a real challenge to work with them, but there's also a revolution going on in AI and machine learning that can help us with tools to make sense of this. So decision support, multi-layer sensor fusion, 3D reconstruction, and so on. And also in the game industry and movie industry, a lot of the tools that they've developed, and I'll talk about this towards the end of the talk, really can provide amazing tools for modeling and data visualization of these kinds of super complex data sets. Another challenge is standardizing drone data and other 3D data. So really one of the shifts that's happened in the last decade is we used to be limited by hardware availability. It was really hard to measure stuff. Now anybody can get a drone and then get a 3D model of their farm, but then the next step is, well, what do I do with this? Or what happened to the data? Or where did my SD card go, right? So there's the fact that we have these tools does not mean that they're widely usable or as effective as they could be. And so I'm excited to be involved with a project that started last year, was also funded by NCRIS, to build a national open infrastructure platform to standardize drone capture and data analysis called the ASDC. And this is really exciting because the goal is to really solve that problem. So, people who are collecting drone data have an open source system and ecosystem in which they can put their data in there. And then, the data is already standardized and made available for all the interesting outcomes that we can think of. And linking projects like the ASDC project really enables exciting large-scale solutions. So, one of the problems is that people solve things either once by a company or once in their own domain, and it's not easily available for other people. And so people end up having to solve the same problem over and over again. But with national infrastructure platforms backed by APIs and web services, you can really enable some pretty great stuff. So in this context, the project that we're trying to get going to put all this stuff together takes the drone data platform, a machine learning pipeline developed by folks in Biga for African lovegrass detection. You bolt that onto the drone platform, which means that natively anybody who flies a drone and puts it into the SDC can immediately put it into this pipeline. If you connect that to ALA, so Australia's Atlas of Living Australia has biodiversity records for all of Australia. And one of the real challenges with machine learning is having enough information to be able to, train a computer to be able to recognize the stuff that a professional can. But ALA has millions of records all over Australia. And so that's a really good tool for providing training data as well as a platform for managing new data that comes into the system. Then EcoCommons is another NCRIS funded project where the goal is to provide virtual labs in a compute environment, and the virtual labs can sit where the data is. So if you have huge data sets on Amazon or on NCI, when you spin up your desktop interface, the compute is happening right next to the data. So you're not downloading these big data sets to your desktop, but you're working with them, where they sit. The other thing about that is if you're pulling in public data sets to do this and you're using that as your development environment, as soon as you're done developing it, so a PhD student is developing some new algorithm, that algorithm already works by design with all of the public data sets. So that bit where it's sitting on someone's hard drive and you have to transfer it to getting it to work with other things is just solved by working within the ecosystem. And so if you put that all together, you get this shared open platform where, any small land care group that wants to look for African lovegrass can already use that. But if there's another invasive that they want to detect, they can train that up. But then when they push it back to the system, it becomes available to everybody. And so it's a way of really scaling small efforts across Australia to be really widely usable by everybody. And on a larger scale thing, the stuff you can do when you have index data like this is really unbelievable. So I highly recommend checking out this Descartes Labs demo. They took nearly 200 billion images of the United States at 1 meter resolution. And they have this platform where you can just click on the map anywhere in the United States on any 50 square meter area and get the top 1,000 matches that are similar to that. And in this case, it's just image pattern matching. But if you think of this in the agricultural context, there are only 1.5 billion hectares of agriculture in the world. So when you have these global data sets like what Planet Labs and Maxar are producing, you can imagine taking that along with environmental data and all the sort of on the ground data that drones are collecting, putting those into one thing, and then having, not just a click on the image, but researchers could say, well, show me, the genetics of all the crops that were planted in these locations, what kind of environment there was, what kind of yield there was, and build that into a turnkey machine learning system. And again, if the data management is handled on the back end as infrastructure, and all of the privacy issues are sorted out, and there's tons of public data, things like this become available just as a tool, as the starting point for when you do the interesting research. So your research project doesn't have to be, how do I stick all this together, but what are the amazing things I could do when I have this kind of data at my fingertips? But it's really important to understand that how you architect infrastructure really has huge impacts on outcomes. And if you look at the internet compared to social media, you can really see a good example of this. So if you think of how the internet was designed, right, it was a bunch of really smart scientists who wanted to move data around between universities. And the goal was that it would be data type and vendor agnostic. As long as you can convert your data into a packet and the hardware can take that packet and reassemble it, that nobody cares. And so what you have with the web is that after all of those layers, the commercialization layer really happens on what you do with all that stuff being available. And if you contrast that to social media, right, Facebook was built where what they wanted to do was monetize that entire process. So monetize your entire social network and all of the interactions that you have on it. And this is really a significantly different way, because if you think of how something like your email works, if I want to switch from, say, Gmail, which I've been using since 2004, to Outlook for my job, all I have to do is put in the data for Gmail servers, and Outlook can access it just like that. If I want to switch off of Facebook, I essentially lose every single interaction I've had with everybody I know and all of my social networks for the last 15 years, because they own all of that data. Can you imagine if your email provider owned all your data and there was no way you could ever get out again? It would seem crazy, but that's what's happened in social networks. And so, I think this is really important to understand, because that's also what's increasingly happening in digital agriculture and all these other places for a whole bunch of reasons. And if we don't build an internet layer for data sharing where the innovation happens on top of that, and you own your data throughout the whole system, you get stuck in a Facebook-like model, which really doesn't provide us the amount of innovation and the sort of healthy ecosystem for startups that you get from a system like the internet. And so it really does matter how we decide to implement this future of digital agriculture that we can all imagine. So, imagine you've solved all those problems and all your data is there. One of the existing problems we still have is that the data visualization and management tools that we have really aren't sufficient for these types of 3D geospatial time series, super dense multi-layer data. We just don't have tools for looking at that in ways that are intuitive. And anyone who's spent a lot of time thinking about big problems or done any research, you understand that you have to unpack all of those things into your head before you can start thinking about them. And you can't pack a millimeter resolution 3D hyperspectral map of 150,000 plants through time into your head with R and MATLAB, right? It just doesn't work. So we need tools that take of those data, organize them into visualization tools that make sense to us, so that we really can do the kind of next gen science that we want to. And I think a lot of the challenges we have now are both around data management, but even when you solve data management, it's around data visualization. So, what we really want, right, is this Iron Man interface where you're working on your computer, you get to some complex 3D data set, you pull it off your computer, and you can interact with it directly. And I really like the Marvel movies, because a lot of their AR scenes are really good. And it makes me feel like we should all be asking, why don't I have the Iron Man AR for my data sets? And how can we build that, and what needs to happen? Because we have the tools now to do that, we just haven't built them yet. And so here's an example of a proof of concept we did. So last year we were waiting for the new HoloLens to show up in Australia. And so we didn't have a HoloLens, so we built a virtual reality model of our office so that you could put on VR and walk around in, it's like the poor man's AR inside the office. And the idea was that, you have this workflow where you have 3D data on your computer. Like I said, you can pull it off. But also, sometimes you may want to also go to the place that you are, where your data is. So in this case, this is a model of one of our growth capsules. It's a high precision growth environment. And so we built this tool where you can, show up inside a virtual model of it. And the idea was that all of the plants on the table there would be parameterized with real world 3D data and so on. And it could also, an AR could provide an interface. So when AR is lightweight glasses, you put on the glasses. If you're the tech, you can walk in there and it'll give you information, in situ within the capsule about what you need to do, say watering the plants. And this year we actually have a 3D scanner. So we're going to be building out this thing, but using like live real-time data. So I'm really excited to do that. And now we have the HoloLenses, so we can do this the way it was intended to be. So one of the other things that's changed a lot recently is that in the last decade, Hollywood and the gaming industry, basically computational tools and our understanding of how first principles with lighting work has shifted so much that they can really start, making models of things that look real. And so you can see these examples on the bottom here. These are from in-game pictures built with a tool called procedural generation, where you basically specify a recipe for an ecosystem, right? So if you want to have an open world game that's made of 1 billion planets or an entire, state in Montana, in the case of Far Cry, you can't just go and place every plant in place like people used to do in the olden days of games. What you need to do is have a system where you can, where you just paint a landscape. So this isn't, you paint open grassland with buffalo in it, and then the system on the fly generates it. You paint mixed species forest, and this is what you get. You can put in weathering and erosion in the rocks and everything else, and the plants can grow using biological principles, and interact with water. But people have not yet used this type of system for biologically based modeling, right? So, but you can imagine, we have the tools now to build this for Australia. And so rather than being parameterized by a game designer, you have the satellite data coming in and the drone data coming in that is on the fly building this model for us to interact with Australia. And that could be our core management tool that sits on top of all of that beautiful data management that we can envision. I highly recommend watching the rest of this video. It's quite cool. So that concept has become much more popular in recent years with the idea of digital twins. And digital twins originally invented by NASA, where they were mocking up space vehicles in case something went wrong in space, they could look at the real thing. But these days, people are using it increasingly to model cities, because as you're building smart cities, it becomes really obvious that, again, you need an interface for collecting that data. And what that interface should be is a model of your city. So this is a project that was completed a few months ago where they LiDAR'd and scanned and photogrammetried all of Adelaide. It's 1,000 square kilometers. It's built in a game engine. They have, they know the locations of every tree. And so all of this is real data put in here. And you can imagine if your smart city data is coming into this, this is like a living real city. And so this is happening a lot with cities, but this is the sort of thing we should start doing for agriculture as the sort of front end interface for how we collect all of that data as a starting point for working with it. And we've been trying to do this sort of thing for a long time, back before we knew what digital twins were. And so back in 2014, when Unreal Engine first became free and VR was just starting to happen, I got a team of students who built us a VR model of the National Arboretum, because we put out a mesh sensor network, but there was really no good way to see what all of that data looked like except in a graph, which was really non-informative. So, you take the digital elevation model and you put it into the game engine to build the base map. All of the heights and colors of the trees are set from the drone data. The trees can change size over time as they grow. And then when you're walking around, you can interact with the trees and see the data on the trees as they pop up. What's cool about this approach is, of course, all the trees have a geospatial location, which if you're in the field, you can use AR to pull up the same data and see it in the field. So you have this neat way where you're bringing the real world into the lab in VR, and you're bringing all your dynamic digital data out into the field so you can see it as well. And more recently, we were working with Houdini. So Houdini is one of these new, well, it's not that new, but it's one of these 3D engines that's extremely powerful. So like when Toy Story 4 came out, they were modeling something like 4 million lights that were doing dynamic lighting of the entire scene. They're tracking 43 million pieces of dust when the characters are walking through a hallway. This happens in, this is done in Houdini. And so what this gives us the tools to do is to build these types of models, but in an incredibly precise way, right? So you can put a DEM in the model like this. So here's a DEM we've added in the trees. You can track rainfall. If your computer is big enough, you can track rainfall down to the individual drop of rain. And what that lets you do then is to start modeling the landscape with dynamic surface flows. And you can imagine plugging this into a system where, rainfall gets increasingly unpredictable and under climate change. So you model your climate scenarios in here, and you can let the farmer know, where they should put new cut lines or where they should do earthworks to catch that rain through time. You can model under various scenarios, where soil moisture here. So if we plot soil moisture as red here through time under, like a 10-year climate scenario, once they've done their earthworks, you can imagine sending a model like this to the bank where they can actually audit what you expect to be able to do with carbon drawdown based on how you've changed the landscape. And again, if this data is done in an automated way, you could do this for every farm without having to do a whole bunch of extra work, right? So what you want to do is you want to build this once to take all standardized farming data. It goes into the model, and then these are the sorts of outputs that you can build for people. And this is all pretty cool. It's really exciting. It sounds a bit far out, but the EU is really fully committed to this. So just around the Christmas this year, they announced that they're doing a project called Destination Earth, where they're going to put in billions of dollars to build a digital twin of the Earth. And the whole thing's going to be open source, which is great because then we can use some of those tools as well. And they haven't fully come up with the funding amount, but they're investing 8 billion euros. So that's something like, getting close to $13 billion just for the computational infrastructure for this. So they're really serious about doing this. And, to demonstrate that this is really possible, global scale simulations like this already exist. And Microsoft Flight Simulator is a really good example of this. So this came out the end of last year. They've built a 3D model of the entire planet with 2 trillion trees, 5 billion houses, and a 3D model of every city on the planet. And because, I don't know, you've probably seen these maps where you can get real-time positions of all of the airplanes in global airspace and all of the boats. So these are all injected into the model, so into the game, so you can fly around right now and watch what planes are taking off from Sydney and what planes are landing. And then they took it a step further and got in touch with this company called Medio Blue that does global scale climate modeling for weather simulations. And so you can actually fly through real weather events as they happen and as your cloud compute. They have a model that has something like 200 million cubes, 60 deep, over the surface of the Earth. And you can see down on the left here, this is what the photos look like when you're in game of real world weather. And it's so good that people have started in real plane flights filming the plane landing and then going back in flight simulator and simulating the exact same flight in the model. So this is the point that they've gotten to. And so, Microsoft already has a global simulation of all of our weather. We should build that. We should build that for farms, and we could build that for Australia because that's a smaller scale than what's already been done just for this game. So final slide, this is just the beginning, looking back when I was a kid, I have a 9-year-old, when I was 9, I had an Atari, I played, adventure with this dragon. This is a dragon, it looks like a chicken. And now my kids can play with real dragons in VR for not much more money, right? So what I think is important to think about is that Microsoft Flight Simulator is really impressive to us, but so was Atari when I was a kid, and we're at the Atari stage and all of this stuff. So right now we're at the crappy chicken dragon version of all of these things, and we need to look forward and think that we can build a future that turns into what we need to really tackle climate change. because in 10 to 15 years, VR and AR will be indistinguishable from reality, right? All of these workflows that are really hard now, they can be automated and plugged into models of the entire planet. And we have the tools to do this now. We just have to decide that we're going to build it and envision the sort of future we want that manages to tackle climate change, because we figured out how to integrate all of our farm systems with everything else. And so, you know, it's a scary time to be alive, but it's also a really exciting time to be alive, because we have all the tools that we need to really tackle these problems. Thanks very much. I couldn't do all this without a huge team of people that all do awesome things on their own and in a team. And so, yeah, thanks.
Wow, thank you, Tim. I'm always amazed by your knowledge and contribution to the discussion. Your work is amazing and definitely opens up many opportunities for
Thanks.
food systems changes. I do have a question here from Robin Alders. Robin said, could nutrient yields over time be incorporated into a digital twin model?
Yeah, absolutely. I mean, that's the goal, right? Is anything that you can think of that you can measure and you can connect with time and GPS location can be put into the map and then pulled out along with everything else. And then it becomes a question of how you actually enable that, how you handle the privacy issues, and you know how you get that data along with the genetics and everything else that's important in a format that you can think about it, which is not an easy problem. But you know, all these things have been solved by engineers for one purpose or another already, right? You know, Tesla's solved half of these problems for their cars already. So we just have to think in that mindset and then figure out how to do it for farming.
Yeah,